I'm going to go ahead and welcome everybody. We have our speaker tonight, Dr. Mi-Ling Li, who's going to speak about pollution in the ocean. Apologize for camera angles and things, but I am struggling with the room camera tonight. So luckily we have another way to do this. Dr. Li is an assistant professor of environmental chemistry and toxicology here at the School of Marine Science and Policy at the College of Earth, Ocean, and Environment. She also has an appointment in the Department of Earth Sciences in the college, as well as SMSP, where she is part of the Water Science and Policy program. Her education, what is an SCD?
Doctor of Science.
Doctor of Science. That's not one I've seen very often. So an SCD of Environmental Health from Harvard. And her research focuses on the intersection between health and earth and environmental sciences. She investigates the sources, transport, and fate of chemicals in aquatic ecosystems that pose risks to human and ecological health. And with that, I'm going to turn things over and mute myself so maybe get rid of that echo. Thank you all for joining us.
Thank you very much for coming on the Zoom and especially in person. So I'm going back to my slides. So today we're talking about ocean pollution. So when we think about ocean pollution, there are many types of pollution. So now you can see the photos, especially people on the Zoom. The left is the fish entangled in this like marine debris. The right is harmful algal blooms. So these are physical, biological type of pollution. So below these two, they are chemical pollution. So chemicals, there are lots of kinds of chemicals in the ocean. They are not as visible as the other two because when you look at the water, you basically can't tell what are they and how much are they, but they are actually very relevant to ecosystem and human health. And hopefully by end of this talk, I will convince you about that point. There are also many types of pollutants, chemical pollutants in the ocean. So I basically kind of broadly separate them into two types. One is metal, or we call inorganic pollutants. The second is organic pollutants. So the metal pollutants are usually, the common ones you will hear is like lead, cadmium, mercury. And today I use mercury as an example because I think it's just really interesting and relevant to our daily life. For organic pollutants, you probably hear about polychlorinated biophenols, so in short, PCBs, because lots of our fish consumption advisory based on the PCB and mercury. And I will actually focus on emerging contaminants, which is kind of a new thing. The long name is perfluoroalkyl substance, so in short, Pfas. So that's something we just started kind of knowing more and more about that and draw lots of attention. You probably have heard from news or will hear more in the future. So I kind of want to give you a snapshot about that as well. In the meantime, I will talk about this is kind of particularly interesting topic in this area, like Delmarva area as well. So first of all, let's talk about metals. So metals, very different from most of organic chemicals. Metals are a natural part of Earth's crust. So they are natural. The heavy metals most of them are very stable. So once we extract and emit it to the environment, they can't be broken down. They just there. And normally, the speed, we have them as like we emit them from natural sources, so volcanic eruption or weathering. These ones are kind of imbalanced with the speed that we cycle that metals back. But anthropogenic activities really disrupt this biogeochemical cycles. In other words, we extract and input way too much heavy metals into the environment than the amount that they can be cycled back. So when we talk about heavy metals, one thing I want to point out is they're not all toxic. There are ones that are biological essential. So for example, copper, iron, and zinc, and the picture on the right and kind of show you the iron is a very important element for hemoglobin, right? So if you have too low level, you'll get anemia. So that's essential heavy metals. What we usually talk about heavy metal pollutants are these non-biological essential heavy metals. So these ones are really, we don't need any of them in our body in order to maintain a normal biological functions. So any of them in your body is kind of extra and not necessary. So here today I focus on one type of metals that I have studied for a while, which is mercury. So if you look at mercury in the periodic table, they are definitely a kind of heavy elements. And they are the only element or metal or that are liquid at room temperature. So that's very special as you know, when the metals. The fact that we have been using mercury for really long time. So lots of time we call mercury as a legacy pollutants. So the mercury, as other heavy metals, they are natural occurring. So the first figure, this picture shows that the rock that contains lots of mercury and the sulfur, it's called cinnabar. So if you want to mine mercury, these are the things we're going for. And the red ones are where the mercury is. So mercury sulfide actually is a good pigment. That's why people have been using it as like a pigmentation and painting for a while. That's mostly kind of a really early time. And they also have been used, so have been found in lots of like Asian tomb. So I believe like people use it as like a symbolic river in these tomb. And if you look at the Greek history, it had been used as for both as like poison and the medicine. So that's really ancient time. Then from history we know that have been used. But in modern time, actually, it's being used even in a wider application. So if you're older or as old as I am, you probably still remember that we used to use mercury in thermometer, in barometer, because mercury expands quite a bit under a higher temperature, right? So it's actually really useful property. So that's why, we adopted it, we use it in the product. Nowadays, most of the mercury in thermometer that this kind of use has been phased out in United States and in general globally. So you probably wouldn't see this anymore. But I remember when I was little, that's something my parents checked if I have fever or not. So the second one, so mercury, the inorganic form is very good antifungal and bacterial growth. So they have been used as a preservatives in lots of medicine. So that's quite common thing as well. They also are very good conductor. So lots of fluorescent bulbs and batteries have mercury. As I said, lots of mercury containing products are phased out nowadays in the United States. But if you go to store, lots of battery now actually say mercury free because they used to be not mercury free. So the fourth one, the function that mercury has is, which is really important, it forms amalgams. So in other words, they can bind and kind of make the kind of dissolve these other metals really well. So that's why it's widely used in silver and gold mining. So that's what people did is if they find some rocks that potentially have gold, and then they put them in a pan, then they pour mercury, liquid mercury into these things. Then the mercury will extract these gold and silver from the rock and form this kind of amalgam. And then you kind of, filter out the rocks that are useless for you anymore. And then you have this mercury gold or mercury silver soup. And what they do, because people want gold and silver, so they heat it up and mercury evaporate to the atmosphere. And the leftover is gold or silver or whichever other metals that they like to have. So that's being widely used as well, and still actually lots of artisanal gold miners are using this tool. And the last one is the same thing, that they because they form really good amalgam with dental filling materials, so they actually mercury existing lots of dental filling. I guess it phased out probably a decade ago, but still, I mean, in lots of people's mouths. So if we take a look at, all-time anthropogenic mercury emissions to the atmosphere, as I mentioned, that it has been widely used in gold and silver extraction. So in 1800, that the North America gold silver run has emitted large amount of mercury to the environment. Then we have relatively quiet time for the war. Then nowadays, it's really the coal combustion, or in general fossil fuel combustion, and the artisanal gold mining that are contributing lots of mercury into the atmosphere. So the coal, the reason the coal and other fossil fuel has mercury, remember, mercury is naturally occurring in the Earth's crust. So anything we burn that we get from the Earth's crust that has mercury inside. So that is these ones are that we emitted mercury basically unintentionally, because the purpose is using other things. You want energy, you want to get gold, but unintentionally emit lots of mercury into the atmosphere. So if we compare this amount with the global mercury that mined since 1850s, so this whole peak and the shaded area, they actually only count a very small amount of the global mercury mined since that time. So this whole chart only equals to the small area of like sun shaded area. And this whole pink area, that means we mined, so we use mercury somewhere. It has not been emitted to the atmosphere. Who can guess where they are now? So they are in the commercial products we talk about. And so you can imagine lots of them either in the landfill if they are already been buried and recycled, or still in your household, and this will be a long-lasting problem, right? So just to kind of summarize what I said just now, that fossil fuel combustion and artisanal gold mining are the major two mercury emission sources in present day, and a lot of mercury still in the commercial products and household items. And before jumping into how they're relevant to like mercury in the ocean, we have to talk about different form of mercury, because mercury actually quite complicated in terms of their biogeochemistry. Mercury has three major forms. One is elemental mercury. So this one is volatile. And they also have an oxidized form, mercury 2+. This is a reactive form. And then this is a methyl mercury, which is the organic form of mercury. This one is much more toxic than the other two. And unfortunately, this is the dominant form in our seafood. So mercury, the mercury usually are emitted, say, from coal combustion or gold mining facility that to the atmosphere, as most of them are elemental mercury, so they're volatile. They actually can be circle around the globe for a really long time. So if you test like mercury in the atmosphere in most of the place, it's basically a mercury from all around the world. It's not, it's really not from a local spot. They have really long resident time in the air. So this partial of this mercury 0, elemental mercury, will be oxidized in high troposphere to mercury 2+. This is the reactive form that could be bring down by precipitation. The mercury 0 actually is not. That's why they can circle in the air for such a long time. So once they become mercury 2+, they could deposit to the land, to the ocean. Then this is another graph that I mentioned that they come from far away. Then they come to the atmosphere. Some of them being oxidized to mercury 2 plus, the inorganic form, then they dropped to the ocean. Then this is the time that in some like relatively low oxygen zone in the water, it's a favored geochemical condition for bacteria to transform the inorganic mercury to the methylmercury. That's a toxic form. That's also the form that's really easy to be taken up by phytoplankton, then biomagnify along the food chain. So when we talk about biomagnify or bioaccumulate, it's really, when we compare the concentration in the water with all the species, along the food chain. So basically the predators. So methylmercury has really strong biomagnification potential, which means if you compare predatory fish, they can have 10 million to 100 million times higher concentration than the methylmercury in the water. The methylmercury in the water actually are very difficult to detect, but in the fish, no problem. It's really easy to detect. So that's also one of the reasons that you barely hear anyone, get poisoned by the mercury poisoning due to drinking water. But lots of time we worry about the seafood consumption. So in general, that the larger the fish is, the longer time they can live, and the higher trophic they are, the fish or marine mammals have higher concentration. And remember, I already said that mercury is a global pollutant. It could deposit to really far away. So that's why in relatively like pristine, we think pristine environment like Arctic, you find a really high concentration of mercury in their biota. Yeah, so actually one of the highest probably is in the Arctic animals. Yeah. So why do we really care about methylmercury? Well, we already talked about it's very toxic, and specifically it's very a potent neurotoxicant. So normally biological system have ability to kind of prevent xenobiotic thing to come in, right? Or like they can barely come across the membrane, because our membrane would consider this is not part of our body, don't come in. But methylmercury can bind this amino acid, this is essential amino acid that our body need, called cysteine. They can bind them and mimic, look like, they are cysteine. So our body actually can distinguish them from the essential amino acid. And in fact, the methylmercury are very good about crossing, basically, we think the most like a defensible barrier in our body, which is placenta and the blood-brain barrier. So the central nervous system is the main target of methylmercury. And as you can imagine, the children and the fetus, they are having this developing stage of central nervous system. So they are particularly vulnerable to this kind of exposure. So we learn methylmercury is poison from a very kind of dramatic environmental disaster. This is called a Minamata disaster. So we got to know this around like 1950s and 1960s. The story is in Japan. There's a coastal town called Minamata City. So there is a factory, a chisel factory there. They release a large amount of mercury sulfate into the water, so via their wastewater release. And even though this is an inorganic form of mercury that quickly methylated to methylmercury, make this the bay water and also the seafood in that area has really high concentration of methylmercury. And people in Japan, I guess in general, and let alone people on the coastline, they eat lots of seafood. And also the cats there eat lots of seafood. And they both go basically crazy. So around like 1960s, lots of people, like they lost their vision, hearing, and speech, and relatively severe cases that people have crippling hand and feet and coma. So actually, more than 2,000 patients have been officially recognized, and approximately more than 1,000 people have died of this disease. And the lawsuit between the people there and the factory and maybe government is still ongoing, and even after so many years. One thing I want to mention is because methylmercury can pass the placenta, so they can pass from generation to generation, right? So I think that's also why this whole impact is still lasting for so many years. Although we wouldn't have such a kind of a dramatic case anymore, because most of country has a regulation about their wastewater. You can't directly release so much into the ocean directly. There are still a problem. I guess many people in the world still have very high methylmercury exposures. So that's my PhD work that I did kind of focus on Faroe Islands, which is a beautiful island, which in kind of between UK and Iceland. It's actually a self-governing archipelagos under the sovereignty of Denmark. So they are because the weather there super windy for most of the time of the year, that they actually can like really grow that much vegetables. They also don't have like a local livestock. Like so there's the researcher coming from them the island that their kid, the first time when they saw a squirrel, they call it dog, because they don't have squirrel, they don't have rabbit. And they start cultivating, the cows and lamb, sheep there, but that's not the normal thing they have there. They just they eat seafood. That's what they do, and that's lots of islanders have as well. And traditionally and culturally that they eat pilot whale meat and the liver. So they do have annual hunt of that, so there are a group of scientists that study methylmercury, we think that the population may be at risk because pilot whale, as a top predator in that ecosystem, has very high concentration of methylmercury, and the people there, been eating them for a while. So they basically, the epidemiologists set up a cohort and follow the women and the baby and over years, and also set up a lot of tests, to understand the potential neurological effects over time. So what they found is that an increased exposure of mercury from pilot whale meat and liver consumption can cause the decrease in fetal development of their nervous system. It also will cause a cognitive deficit in young children with the prenatal exposure to methylmercury. So in other words, their IQ will be lower than their peers. And also for adults, there could cause increased risk of cardiovascular disease. So this is actually really important and solid evidence, and that's one of the very important evidence base that our US EPA actually kind of based on when they developed the reference dose of methylmercury exposure for US population. Yeah. So just kind of plugging a little bit that not only the Faroe Islanders. So my current work actually take a look at the global subsistence fishing populations. By definition, they fish for food. And we found that most of these populations are at risk if we use US reference dose that's established by EPA. So this is, kind of really show based on the current level of methylmercury in the ocean, it still poses direct threats to many populations in the world. So how about US general population, right? I think that's most of people are kind of interested. So we started a project that we basically take a look at in general, like a seafood commercial market in the United States. And we take into account the import, export, and domestic landing. So the leftover is the ones that we really consumed by US population. What we found is, first of all, this country really gets seafood from everywhere, all the ocean basins. So basically, you get methylmercury from all the ocean basins. Again, highlighting it's a global problem, right? And in addition, that for the US, if we break down to different seafood category, which I made a bar chart here. So different color of the bar are just different fish harvesting region. And the height of the bar means, how much percent of that seafood, how much percent of methylmercury total intake is from that specific species. So I guess we have a poll that we can open on the Zoom. And also, I guess you guys just think about what we just talked about, predatory fish, these things, and think about how, because methylmercury intake is a two-factor, right? How high the concentration in the species, how much you eat. So also think about, how much you eat, or your neighbor, your friends, kind of representing US general population. Which answer you think would be? Any guess? How many think of B? How about the ladies? A. Okay. Sorry? B. Okay, so we have 3 B and 1 A, and I don't know how many. Maybe we give a little bit, like 5 more seconds for yeah. Welcome to have other answers if you have, and then we can.
In a minute, 70% people answered.
Oh, okay. Yeah. So we have more B here. So how about you?
Yeah, mostly tuna.
Okay.
80% for tuna, and the second was salmon.
Okay, so well, it's quite matched, right? So I guess people are knowing like tuna, because they both big fish, right? But the one thing I want to mention is, so the answer, I guess, let me go to the answer first. The answer is tuna. So the reason, so we eat them a lot, first of all, it is true. But the main reason is tuna has much higher concentration of methylmercury than the salmon. So remember, they both top predators, but salmon usually only live maybe 3 to 5 years. Tuna could live 30 years easily, right? And also, I guess there's also where they live that make a difference as well. But in general, salmon doesn't have high methylmercury concentration. It's actually relatively a healthy seafood choice. But I guess most of people, I think, good job. And so I guess we get into species level. And for this country, you can tell most of the methylmercury is actually contributed by basically one big group. Lots of time when I go to conference and people would ask me this question, which fish to eat? Because methylmercury basically is in all kinds of seafoods. I don't want the message would be like don't eat seafood. Fish has chemicals inside. They also have lots of important micro and macronutrients that are beneficial to human health. And more important that some micronutrients, for example, omega-3 polyunsaturated fatty acids in fish that actually can reduce the harmful effects of methylmercury exposure. So they actually have a counter, effects. And the most important, I think everyone should remember, is fish that is high in methylmercury are not necessarily high in omega-3 fatty acids. So you can be wise about what you eat, right? You can try to maximize your benefit and minimize your methylmercury exposure. And at individual level, because we can actually change the seawater methylmercury concentration overnight, or the seafood methylmercury concentration. But what we can do is we can be wise about what you eat, I think. So this is the FDA and EPA actually developed a kind of fish consumption advisory. So if you Google, FDA fish consumption advisory, that's published in 2017, they actually tell you the best choice, good choice, and the bad choice. So they will tell you avoid big eye tuna. And the salmon actually is, I think, one of the best choice, if I remember. And also, yeah, because salmon is fatty and it has usually has lots of omega-3 fatty acids. Yeah. So that's something I think we do like, individual level, but what we can do at a global level, right? Because it's a global pollutants. especially for United States, we get fish from everywhere, right? It's the fish. In order to reduce the human exposure, we really have to have global regulation, right? And I want to end this part with the kind of positive note that there is a global legally binding Mercury Treaty, which is the first time that there's a treaty, a global treaty as just for one element. It never ever happened. It has been, scientists and the politician and the non-NGO, all these people have been working for decades to get that happen. And what this means is in 2013, there are more than 100 countries that signed the treaty. So they agree to reduce or minimize mercury emissions in their country to atmosphere or to environment. And this convention entered in force in 2017. And I checked yesterday that 137 countries ratified. So this is the map here, that the country that ratified. So the ratification means that they have already have their own national regulation in place, and this reduction of mercury emission is happening, which is very promising. And hopefully in the near future, there will be a long list of good choices of seafood, right, for us. So for the rest of the tonight, and I want to talk about another type of contaminants, which is the organic pollutants. In short, it's called Pfas. It is very different from mercury because it's not natural occurring, it's totally man-made. And second, we know relatively little about that. And the mercury we have been studied for a while. This one we studied since 2000, so it's quite relevant. And the scientific evidence is just coming out quite rapidly. So just in case you like molecules and like these photos, that the Pfas is a type of a very larger group of chemicals that they all have like this carbon backbone, and they connected with fluorine atom. So this is problematic because the carbon fluorine bond is probably the strongest bond in organic chemistry. It's very, very hard to break them down. We can't find microbes or something that in natural ecosystem that can break them down. So make them super persistent in the environment. And some of them are bioaccumulative, which means you will find the tissue concentration in the organism higher than the surrounding environment. We actually call it emergent because the science emergent, we have been using it again for a really long time. And it's in 1940s, DuPont was the first one that produced and marketed under their trademark that Teflon. So it's we have been using them for a while. And so since 1940s, there are lots of other products that have been using this whole group of chemicals. And the reason we use them is it's really good surfactant. So it's water and stain repellent. So it is really useful. And I mean, I'm glad that, we found that property. And now over 10,000 unique PFAS have been used in technical application and consumer products. And you can imagine, right? Stain and water repellent, really good for food packaging. You don't want the oil or water, penetrate when you get something from Starbucks or something. And household items, makeup, eyeliners, lipstick, lots of them show that they have PFAS inside. Dental floss, stain-resistant furniture, carpets, they also have PFAS, and non-stick cookware that have been known for a while. So if lots of time you go to store now, they would say PFOA free or PFAS free, that because before they use that. So another huge contributor is firefighting practice, because PFAS widely existing in the firefighting form. And so the airport or military bases are usually the point sources for PFAS. So just a kind of recent study that published in late March this year, that they found PFAS widely exist in most of the food packaging in the kind of fast food chain that we see all the time. Some even claim they don't use that, but no, it's being detected. So just give you a little bit of sense that this is kind of everywhere almost. So from consumer products or industry, eventually PFAS come to the waste infrastructure, right? And the waste infrastructure, again, these compounds are so hard to break down. The waste infrastructure not designed to break them down. And they become like a source that they collecting them, they enriching them, then they release to the environment. And so wastewater treatment plants or landfill are usually also upwelling sources for PFAS. And eventually these PFAS, you can imagine, transported via the surface water or groundwater, then to the coastal area and the ocean. So why do we care about PFAS? Lots of studies show that with high certainty that PFAS is toxic in different ways. It's associated with many kinds of cancer. It reduces the birth weight, and it can be a very strong immunosuppressant. Means like your vaccine wouldn't work. Because the PFOA and Pfas are two types of PFAS that have been well studied, and because of the health effects that they have been listed under Stockholm Convention, which is a global convention for kind of phasing out the really toxic persistent organic pollutants. But again, Pfas has 10,000, more than 10,000 compounds in this, and the majority of them has not been regulated yet. But just in case, if you want to know more history about, PFAS application, what kind of health effects is, there are two movies and I would recommend, maybe that would be some fun on the weekend for you. That one is the dramatic one called Dark Waters. And the other is documentary one called The Devil We Know. Both available online, and I found both are well made. So how are we doing in terms of PFAS for human exposure? I mean, not so well. So this is a study that they look at a population we call NHANES. So it's a National Health and Nutrition Examination Survey. So the CDC actually survey people that representing US general population every couple of years for their nutritional status, health status. And they found 95% of that population, which representing US general population, has PFAS detectable in their blood. Again, these are man-made things that we don't really need any in our blood. And I saw new studies that are coming out as even higher percentage. So essentially everyone here that have PFAS, have exposed to PFAS. And in terms of where you really get them, it really varies depending on where you live. So if you live in a place that drinking water has been polluted by PFAS, then drinking water is probably the main source. But if you're not living in drinking water contaminated area, then predominant pathway is probably food. That could be from by accumulation in the seafood. That could also be these packaging that eventually the PFAS get onto the food. So right now, we don't really have a national regulation. They talk about this for a while. We still don't have a national regulation for PFAS. We have health advisory. So I said this is outdated. I just want to show you why this is still important. So until last month, we're still using US EPA's 70 ppt, so nanogram per liter, for PFAS and PFOA maximum level as kind of a national level. And we all know from epidemiological studies that this is too high for protecting human health. That's why all these states that have lower concentration or stricter standards for their drinking water or surface water. And I think the Delaware one is coming up and very similar to what New Jersey has. It's around 10 ppt. But last month, US EPA actually issued a new interim health advisory and the final health advisory for another 2 types of PFAS. But if you compare PFOA and PFAS, previously there was 70 ppb. Right now they are orders of magnitude lower. They are so much lower that most of the waters in the country probably cannot achieve that. But I just want to tell you why they get this. So they got this as they consider as safe level because that is from an immune toxicity study in children. And they back calculate how much the maximum level of drinking water should be for protecting the most vulnerable population. So as from a public health perspective, that's totally valid, right? But that also shows, because 70 ppt maybe most of the place in the country can accomplish, but the less than 1 ppt, most of the place can't. Like probably, I test my lab water, that's not, it's exceeding that level. So it just kind of emphasized how far away we are from protecting human health from PFAS exposure, and that's definitely the goal. One day we will get there. So for Delaware, I think we particularly have some kind of interesting perspective about PFAS or history about PFAS, and I think the 2 major issues that we have. One is we have limited data in Delaware. So this is a map that you can go online. It's EWG.org. They have an interactive map that anywhere they sampled or they collect data from like a place that's sampled for drinking water or groundwater, and every data points on the map just shows you like they sample there. There's data, so it doesn't mean it's necessarily being polluted. But you can tell that Delaware is pretty empty and not so many data there, right? Like I believe Denmark is working on that, but we still kind of slightly behind with compared with New Jersey. And among the ones that sample are very concerning. So I was saying 70 is too high. These numbers are not something you like to see. And I believe the Artesian water company that's in Newcastle, they have already installed the filters because that's not something they want to supply people. But they have been supplied water for a while. And the Blades, which is not far from here, their water is polluted by, I think it's a local industry. So that's higher than the old EPA health advisory. Therefore, they become a Superfund site that EPA and I think collaborated with Denmark are cleaning up now, that site. So compare with drinking water. So most of these are drinking water, groundwater. There are fewer data actually in the coastline. So this is the one I can find relevant to our area. So they sample seawater, inshore, offshore, from New England to Mid-Atlantic. Then they found that who has the highest, right? So it's right outside of the bay. They didn't sample inside the bay. So right outside the bay of Delaware Bay, that is the highest among, along this coast. And the runner-up is Chesapeake Bay. So kind of highlighting, regionally, we probably have big issue of this. But not so many studies actually are like following up, like published yet. So that's the only thing I can find. And that's also something that really kind of struck me. And when I started a little bit over 2 years ago at UD, I decided to take a deep look at it, especially what happened in the Delaware Bay, right? So the question I have is, how is the distribution of PFAS in the seawater, in the sediment, in the bay, and how high the concentration in our marine organisms, and how are there any species that are particularly vulnerable, or in other words, have much higher concentration than others? Because these questions directly relevant to human health and also for animal health, right? So that's something in my mind, and we applied for a sea grant, and that's ongoing research that funded by Delaware Sea Grant. We have sampled a little bit in the Bay, and the plan was, going through the whole food chain and sample environmental samples and biological samples. So far, I don't really have data for you guys, but a year from now, I should have plenty of them. And so, if you're interested to know more about PFAS levels, of the fish from the Bay, stay tuned. Maybe come back next year around this time. Yeah. So I think that's basically all I have today. And I do want to acknowledge my collaborators and especially people from Delaware Sea Grant, the Chris Hauser and Ed Hill. I started my career at UD during the pandemic without knowing much about the state, knowing much about people here. So these two are really directing me to lots of helpful resources in Center for Inland Bay, Delaware State, and DANRAC. So I'm not going to say every of the name here, but I'm truly appreciate their help. Also, John Cohen's group at UD, they've been our field trip buddies for a while. So yeah, special thanks to them as well. The work I presented about mercury is funded by US EPA. And I want to thank my collaborators at Harvard and UBC as well. So I think hopefully we're on time, and I'm happy to take questions or comments, suggestions.
Does anyone measure the mercury levels right out here in our waters?
Mm-mm.
And or grab a fish or two and measure the mercury that they catch right here?
I don't think so. So the question is, anyone measured mercury from this area? I think there is, if I remember correctly, there's a study in Chesapeake Bay. There's a study in the Long Island Sound. I don't remember there is a particular study in Delaware Bay, especially about fish. But I believe at least the river fish, like the freshwater fish, is definitely monitored in terms of their mercury level. Their PCB level are monitored by DANRAC. And that's why for recreational fishers, make sure you check out the state level fish consumption levels, because that's mercury and PCB are monitored by most of the states government. Yeah.
So we have a lot of questions online about mercury, but maybe we'll start with the PFAS one.
Okay, yeah.
And work our way backwards. Actually, two. Another one just came in. So Lee Altmaier wants to know how, I would say, like, is it possible for less than a part per trillion concentration be measured and controlled for PFAS? Like, is that a useful number? If the limit is 0.004 PPT, is there any way to detect and do anything about levels that low?
Yeah, so far, based on the EPA methods, which is, I think you filter 250 ml or 500 ml water, and then kind of you enrich them and kind of measure the concentration. For lower than 1 ppt level, I think for most of the instrument, over the world, are not that sensitive. Yeah, so I just want to stress that health advisory is simply based on the health effects for protecting health. So they haven't taken into account in terms of regulation, feasibility, economically, any replacement in the future. We always say risk assessment and risk management are two different things. And in terms of how we're going to manage it, and what's the regulation would be, because this is health advisory, right? I think that's a question for EPA, and I think they are actually have quite a bit hearing and information session that I mean, at least last month I saw one, and this month there's an upcoming one. My guess is they try to have this health advisory, just let people know this is a safe level, and then they also will have a screening level, which is like, we really have to do something. And I haven't known that level yet. I think that probably is coming out as well. But that's a good question. basically can't detect if that gets that low. But I guess unfortunately, most of waters now I'm testing, it's definitely above it's detectable. So I don't know if it's a good thing or bad thing. As a scientist, it's a good thing. You get a number, but as you know, as a public, it's not really great. Yeah.
The other PFAS question we had, which will kind of get to some of the mercury questions too, is there any way to filter these contaminants? Is there a way to remove what is in the water?
Yeah, so as an end user, household, the RO system, the remote osmosis system, or even just carbon filter, you can't get all of them out, but it's quite efficient. Yeah, so you can do that. I think I would recommend if you suspect your water as kind of contaminated, or you kind of worry about your water, I would suggest filter it. And most of filtration system actually could work. The difficult part is water in the ocean, water in the natural ecosystem. What can we do with it? That's something I think lots of scientists are thinking about that a lot. Yeah, but as a small scale, it's doable. Yeah.
That was one of the questions. Switch to mercury. Somebody was wondering whether there's a way to remove mercury from the ocean, and followed up. Regardless of whether there is or not, is there a way to remove it from food before it?
That's a very good question. I don't think there's an effective way to remove mercury from food because mercury bond to protein. So unless you don't eat mussel, fish fillet or something, then we can't get rid of them. So PCB is different thing. Like PCB, they kind of concentrate in the fat. So lots of time people will suggest if you worry about PCB, you kind of skin off and get the fatty part off. Mercury, you just can't do anything with it. It's there, it's there. Mercury in the ocean, not any engineered way that you can deal with it. I mean, heavy metals, like basically just wait until, they absorb to biota particles, then they sink to the ocean basin. Then over time, it's the sediment barrels and they become a deep ocean, kind of a sediment and never come back. That take a really long time. So that's why mercury is so important to cut the emission, because we just don't really have very effective way. Although for point sources, co-combustion and these facilities, they can. So that's lots of countries. Remember, we have the treaty. So they install some scrubber to kind of remove mercury, absorb mercury before the air goes to the atmosphere. Yeah.
Is there any way, just jump in and you guys come up with one. Is there any way to check for mercury in food? So it can't be removed. Is there any way to know?
That's a good question. Well, I mean, scientific lab can do that, but I don't think normally like any industrial, yeah, it's not something I feel like you go to a store or something that they would tell you that. I can't think of any source of that. But again, I think most of the fish that if you follow the rule of like don't try not to go with this really high trophic level predatory fish, and try to follow the fish consumption advisory posted by FDA, it's actually quite predictable in terms of the concentration of mercury in the fish. Yeah.
You mentioned that the PCB concentrates in fat.
Mm-hmm.
The mercury concentrates in protein.
Yeah.
So that's kind of known. That was a question we had, but just making sure I heard that you had just answered it anyway.
Yeah.
Diane asked that question. She also asked if chelation can help with decreasing mercury in humans. So
yes, that's one way people does.
A treatment.
If for people who has really high concentration of mercury in their blood, usually there's already show some effects. Yes.
And so for the rest of us, can you explain chelation?
I think it's chelation. So it's I believe it is something that's like kind of chemicals that they try to basically, I actually never, I never did that, but I believe it's also like an IV or something. It's like a safe level, and they kind of try to bond the mercury from your blood, and then kind of get rid of it, probably from urine or feces. It's so that it doesn't keep circulating. So basically, you kind of inject something that's like kind of as a binding or absorbent into your body. Yeah.
It draws it out.
Yeah, exactly. Yeah. But normally I think people have very high concentration that they would do it. I know one person is a billionaire and he eats like sushi every day. It's probably all tuna every day, and they keep passing out. And they went to hospital and found so usually mercury, it's easy way to test it, just test the hair mercury concentration. That was probably like 50 times higher concentration than normal people. And they start the chelation. Yeah.
I'm just gonna finish Diane's list here. She had one more. She was asking, is autism related to mercury? I think that might come from the vaccine, the debunked vaccine study from '98, but you're gonna address that?
It's very controversial.
Yeah.
And I think my takeaway is I don't directly do the autism and mercury study, association study. My takeaway is the vaccine or whichever medicine that has a higher benefit than the pros that's way higher than the cons. I think lots of time, because mercury now we try to phase out. So I think less and less vaccine will have mercury, first of all. Second, I don't think there is a strong evidence so far that these two are correlated. So I guess the evidence, maybe one study show yes, the study is not. So it's like really inconsistent. So I wouldn't really think it's I don't prove it's a solid association. But I guess everyone can have their own take about that.
So mercury is known to be a neurotoxicant,
Mhm.
but not known to have a relationship with autism. That's still being investigated, essentially.
Exactly. Yeah.
We've got a lot of practical questions, which we would expect in a talk about pollution. Somebody mentioned from very early on. Give one there.
Yes,
Yes.
cited the example of the millionaire eating the sushi. Does the mercury level go down in cooked fish as opposed to raw fish?
Not that much. Yeah. So mercury really stick with the protein. People tried like grilling, like different cooking methods. People tried with different herb or different thing. There's no strong evidence that they can remove it. Although that which is really understudied is people were saying maybe after cooking or after certain methods that the bioavailability, which means like how much you have. So when you look at the fish, how much mercury is still there. Like I don't think that will have any decrease or a significant decrease. But when you eat them, they may actually interfere with absorbent or uptake from the body to take the mercury. So say, originally mercury was believed to have almost like 98 or 95% of absorption rate, which means essentially what you eat or go to the blood. But maybe these one can decrease the efficiency. That is totally under investigation. But that's something we're really interested, because that could be kind of prevention or strategies for public health. Yeah.
Somebody online, Vivian, says she has a red card box that looks a lot like the one in your slide early on. She's wondering about what kind of danger that box or things like that might have. So
The
things,
box?
with the red, mercury, the colors that have been used for. It does depend a lot on how that red was made. But maybe just generally speaking, how much of a risk is thermal absorption of mercury? somebody else was asking about actually the mercury in CFL light bulbs, right? CFL.
Oh, yeah, the light bulbs.
So if you
yeah.
break your light bulb, how much do you need to worry, right? These contact issues, are they
Yeah.
serious for mercury?
So again, the most toxic form of mercury is methylmercury, which is in the seafood normally. The light bulbs ones and the paint or whichever, if they, I don't know what's the paint made of. If they have mercury, it's likely the inorganic form. So first of all, they're not that toxic. So I mean, don't lick them, don't eat them for sure. But I wouldn't worry too much about the thermal exposure. If you have a light bulb that has mercury inside, if abruptly it just broke, then I would just make sure the ventilation is going on. Then dispose them. I wouldn't worry too much about inhalation as well in that case. And the thing usually as a scientist we worry about about the say red chips containing paint containing mercury or other things containing mercury, even as inorganic as how it recycled, will that be going back to the environment? So that's something I feel like I would be more worried about for the environment, not that much I think for the human health perspective.
It's 5 after, but only a couple more questions.
Sure,
here.
yeah, go ahead.
You guys are game. We'll go ahead and get through the list. 2 questions about where else mercury can be found. Well, you mentioned it's in the atmosphere, but I think they're asking about is it maybe lower in the atmosphere, and then wondering if it shows up in snow. So you said it can precipitate, but that was
Yes. So if you like in the rain, in the snow, yes, I mean you can test that in seawater, but these are inorganic form and usually very low concentration. It's really they have to go up to the food chain and go a million times higher. Then that gets something worried. Yeah.
And the last question was actually one of the first ones to come in. I haven't given it to you yet because I'm not quite sure how it fits in, but it was about your early slide about metals in the body, metals in the human body. You kind of made a distinction there about ones that are essential and non-essential. They're asking about lead. Is that on the list, I guess?
Yeah, as non-essential. Yeah.
So they're asking, isn't that very toxic? Which it is. So that was your point, right? The essential ones we use in our body, the non-essential ones, including mercury. Right?
Yeah. So, well, I guess that's all the way.
I think it was really early on.
Well, so yeah, so that's a good catch. I didn't go into detail about this, but yes, so cadmium, lead, they both toxic, and especially lead. I think you probably hear from clean drinking water issue, all these things. I mean, still ongoing. Lead is also widely used in the paint. Because it's red as well, right? So it's lead. I would be more worried about drinking water. That's the main source. Lead doesn't bioaccumulate or biomagnify in the top predators. So usually seafood, you don't need to worry about that much about that. Yeah.
I think that was kind of an establishing question about the argument here is non-biological essential means we just don't want any.
Right, non-essential ones. I mean, ideally, we don't need any of them. We don't want any of them. Yeah.
There we go. The joys of Zoom. We've been doing this for 3 years and we still haven't quite figured out the best way to do it. But I just wanted to thank Dr. Li for sharing all this with us tonight. It obviously was a presentation that got a lot of attention and interest, and for good reason. So I know I learned some things, both kind of interesting and academic and practical. We did send out the link for the chart she shared. Hopefully everybody found that, and hope everyone will join us again in 2 weeks' time for our final online only Zoom, August 11th. I forgot to look up who's speaking. No, he's the final in-person one. We have one. Oh, Kyle Davis. Kyle Davis from our Department of Geography and Spatial Sciences is speaking on food.
It's also about food.
Yeah, it's another food one. So sign in for that. And then August 25th, actually, that's a good point I'd like to pitch to everyone here and at home. August 25th is our final in-person lecture here in Lewis. Mi-Ling Li will be speaking on his new book called Earthly Order: How Natural Laws Define Human Life. We will have a book signing afterwards. So Browse About Books will be here to sell those, and a little bit of a reception where we're hoping to maybe even get some of our prior speakers to come down just so everyone can meet and chat with folks. So put August 25th on your calendar, but before then, August 11th online, we'll see you back here for Kyle Davis. Thanks, everyone.